In this collection of videos, we are going to begin discussing volumes of revolution. Now, before we get started with a lot of equations, I think it's really important to understand where those equations are coming from and how the mechanisms that we'll be using to study volumes of revolution are really the exact same mechanisms we used when we were studying integration and area underneath the curve. So to show you what I mean by that, I'd like to review what the process of integration was and how we ultimately came up with the notion of a definite integral. The idea was we had some sort of shape that was carved out in space by a function. In the example that I'm showing right here, the function that I'm using is the square root of x, given by this blue function right here. What we were interested in doing with that function was finding the signed area between that function and the positive x-axis. The way we went about doing that was to use basic shapes, and the most basic shape we could think of was a rectangle, where the width of our basic shape was defined by taking the whole length of the interval we were considering and asking how many rectangles we wanted to place underneath the curve. In this example that I've drawn, I'm working on the interval from 0 to 4, and I wanted to put 4 rectangles underneath the curve, so you can see from the units on the graph that each rectangle has length 1. If I put more rectangles underneath the curve, so here my variable n is standing for the number of rectangles that I want underneath the curve. 4 here is representing the length of the interval. And so this thing that I've called step, which is really the width of each rectangle, is given by taking the length of the interval and dividing it equally up into the number of rectangles that I'd like to place underneath that curve. And what's nice about Mathematica is that putting these 3 things all in a row, I can just reinitialize that cell and it will update my picture to demonstrate that change. So we're placing rectangles underneath our curve. The width we're getting in a straightforward way by just taking the length of the interval and dividing it up by the number of rectangles we want so that each rectangle has the same base length. However, what's defining the height of the rectangle is the height of my function at some point over the width of that interval. And so our rectangles have equal base length but varying height. The height is defined by the function that we're considering, and what we do is compute the area of each of these individual rectangles and then add them all up to get an approximation for that area between the function and the positive x-axis that we're looking for. And the story went that as we put more and more and more rectangles underneath that curve, you can see that the gaps between the function and the rectangles are getting smaller and smaller, and our approximation is getting better and better. So the very calculus way of thinking about those sorts of things is to say we're going to take a limit as this n value is going off towards infinity, and that will switch us over from finite sums into these infinite definite integrals. What I'd like us to think about in terms of volumes of revolutions is taking this same machinery, but now rotating or revolving this picture that we have to cut out a shape in 3-dimensional space. Now, what's really cool about Mathematica is that Mathematica can actually help you visualize that process. If I switch from this beautiful graph that I'm looking at to looking at one of Mathematica's command called revolution plot 3D, you can see right here that the shape I have is the same as that square root of x function. Now, I don't have the rectangles pictured here, we'll get to that in just a minute, but I have this square root of x function drawn right here. And this function in Mathematica, revolution plot 3D, is meant to help us visualize what happens to this function as we revolve it around an axis. So in particular, I've got this angle variable that right now starts at 0 and then doesn't stray very far away from 0 at all. I just have it set to 0.01. So I've only started to turn my function a little bit, and it gives the illusion of my function not being turned at all. As I change that value and reinitialize the cell, you can see that now this function has kind of jumped out of the computer screen at us a little bit and moved a little bit more significantly and noticeably. Mathematica also lets you click on a visual image in three-dimensional space and turn it so that you can see it better from whatever angle you prefer. If I make this value something like pi/2, when I update this cell, what comes about is this visualization of a quarter turn of that function from here all the way down by 90 degrees. And if you spin that visual, you can see very much what's there and what isn't coming out of the screen at you. Rotating the full 2 pi degrees that make up a circle and reinitializing, you see that we get this whole bowl-like shape that we should expect to see if we were to take this curve, y equals square root of x, and rotate it around the x-axis. We would go from this shape to this shape. So the goal in our volumes of revolution section will be to take a curve that's defined in the plane, something like the square root of x, and to imagine that we've then rotated that entire curve all the way around some sort of axis of revolution. In this example that I've been considering, I've been rotating around the x-axis right here. The way that we are going to approximate the volume that is enclosed by this surface, so all of the stuff that would be inside that bowl there, is by visualizing spinning our rectangles. Taking our rectangles and rotating them around the positive x-axis, we'll be able to determine the shape that's obtained when we do that, and we'll be able to find the volume of each of those individual shapes. Adding up the individual volumes will give us an approximation of the volume of revolution obtained by rotating the function, and so that's the approach that we'll be considering. To better visualize the shapes that we obtain when we take our rectangles and rotate them around an axis, I'm turning to this more interactive tool straight from Wolfram's website. Here, our function is the square root of x. We have 4 rectangles on the region as x goes from 0 to 4, approximating the area beneath the curve y is equal to the square root of x. And what's happened is each of those rectangles has been spun around the positive x-axis, and you can see that each one of those rectangles, when spun around the x-axis, is giving us a cylinder. A cylinder is a very basic geometric shape, and so it will be very straightforward for us to determine the volume of each one of these cylinders. To see how these cylinders approximate the solid of revolution, we can now actually rotate our curve, and you can now see the blue cylinders all sitting inside the red bowl-like object that we've seen, and you can see the way in which those cylinders approximate the volume of our entire shape. And just as it was when we put rectangles underneath our curve, the more and more segments or cylinders that we add to this process, the closer and closer the approximation becomes, to the point where you can see very little difference between your blue cylinders and your red surface.